Hello there. This is the video for sections 8.1 through 8.4. And the main learning objectives I'm going to show you in this video are how to construct a hypothesis test for a population parameter. And I'll tell you what a hypothesis test is. We're going to determine the conclusion of our hypothesis test using two different methods. One's called the p-value method, and one's called the test statistic method. Your homework's going to ask you to demonstrate that you can use either one. But when it comes time to do like a midterm or a final, you could just focus on the one that you prefer. The third learning objective that is important for these sections are to be able to clearly and precisely explain the conclusion of a hypothesis test using the scenario context, using the word problem words. So being able to write a correct and precisely clear conclusion is really kind of an important goal for statistics students. Lastly, we're going to identify and explain two types of errors labeled type 1 errors and type 2 errors. Nothing exciting about the names. We'll explain what those are because it is kind of important to know that there are possible errors in hypothesis testing, as in with all parts of statistics. That's why we only have a degree of confidence, not 100% confidence, because it is possible that our conclusion is not correct. All right, so for the first three learning objectives, I'm going to do them all sort of together since they all are related to each other. And the last objective I'll do at the end of the video. So the first three, just once again, we're going to construct a hypothesis test for a population parameter. To recall, a population parameter is a measure about a population. We typically measure a proportion of the population, the mean of a population, or a standard deviation of a population. Those are the three things we typically construct hypothesis tests for, and those are the same three things that we constructed confidence intervals for. The second objective is to determine the conclusion using two different methods and to explain that conclusion in clear language. All right, so let me tell you a little bit about what hypothesis testing is. So I have a little blurb here about that. Hypothesis testing is actually similar to confidence intervals, which we studied in the previous chapter. Both procedures use a sample from the population to make a statement about a parameter of the population. So if I'm trying to make a statement about the proportion of a population, I look at a proportion of a sample of that population. If I'm trying to make a statement about the mean of a population, then I take a sample and look at the mean of that sample in order to make a statement about the mean of the population. This idea of a hypothesis testing is to determine whether or not our sample provides enough evidence to confidently dispute a given claim about a population parameter. So if I read that backwards, there's going to be a given claim about a population parameter. We're going to see if we can confidently dispute that claim. So there's only two options. We can confidently dispute that claim, or we cannot confidently dispute the claim. There's only two options. I'm confident I can dispute the claim. I'm not confident I can dispute the claim. And how are we going to get enough evidence? We're going to get a sample. And based on the sample, we're going to see if there's enough evidence to confidently dispute that claim about the population. All right, so let me give some specific examples without going a lot of numbers. So I'm going to give you just a basic idea of how hypothesis tests work and how to write them out before doing any calculations or trying to see if we're confident in disputing a given claim. So my first example here, suppose that a magician, or if you're wondering where I am on the notes here, I'm right here. A magician gives me a coin and claims that both heads and tails have a 50% likelihood of resulting from a random flip of the coin. And I'm wondering if the magician is trying to deceive me. So what I do is I flip the coin 20 times and I note how many tails there were and how many heads there were. It turns out in this particular example, I got 15 tails and 5 heads. Now, 15 tails, I mean, we would say that 10 and 10 would be like expected, but like if you flip a coin two times, I'm expecting to get one heads and one tails, but we're not totally shocked if we get two heads or two tails. I mean, that's going to happen sometimes. So the question is, when I flip this coin 20 times, I get 15 tails and 5 heads. I mean, certainly that's far away from the 10-10 I was expecting, but is that so far away that it's not just due to random chance, that there's something suspect about this coin. So the question I have is, can, after this flipping of 15 tails and 5 heads at 20 flips, can I now be 95% confident that I have enough evidence to dispute this magician's claim that the coin is actually a 50-50 coin? So to do this, what we do is we define a variable. In this case, we're looking at proportions. P is the common letter we use to define a proportion. So we say, let P be the proportion of tails that just results from flips in general. Our null hypothesis is always written with a H sub O, and it's always written with the equal sign. In this case, our null hypothesis, which is what the magician's claim is that the proportion of tails is 50%. So the null hypothesis is always what the claim is, and it's always written with an equal sign. Okay, next is what we believe might be the alternative to the claim. So the magician's claiming 50-50, we're saying maybe not. So maybe not could be more tails or more heads. We're just pretty certain that it's not a 50-50, or at least we're not certain. We want to see if we can be certain. We want to see if there's evidence that says that it's not really 50-50. So what we have is an alternative hypothesis. Alternative hypotheses are always written with a not equal sign or a less than sign or a greater than sign. In this case, we write it with a not equals to. We're not really sure if there's going to be more tails or more heads. We just think it's not going to be 50-50. So our alternative hypothesis, H sub 1, is that the proportion is just not 50. By the way, many books use HA instead of H1. There's different ways of writing out what the null and alternative hypotheses are. So just be aware that sometimes the notation changes, but the wording alternative hypothesis, null hypothesis will remain unchanged. All right, so as I've said, I'm not going to go through the math right now. We're going to do it later in this video, but the idea is we're going to use our statistical formulas to determine whether my sample of 15 tails and 5 heads provides enough evidence that we can be 95% confident that the magician's claim is incorrect. So that's the sort of background, that's the strategy for how a hypothesis test is. There's a claim, there's an alternative to the claim. We write out the null hypothesis. Oh, first we define our variable. We write out our null hypothesis. We write out our alternative hypothesis. And then we do some math to see if we can be confident that we can reject the magician's claim. All right, let's do a couple more examples. So that was an example with a proportion. Well, the claim was the proportion was 50%, and we said, nah, we don't think so. Here's a second example. Suppose I have a friend, and my friend says that the average height of an NBA, that's a basketball player, is over 7 feet tall. But I feel that number is too high. I know there are definitely lots of players over 7 feet, but for the average to be over 7 feet, I'm wondering if that claim is actually incorrect. So I need to define a variable. So in this case, we're looking at the average height. Average is a mean. So our null hypothesis doesn't use the letter P because we're not looking at a proportion. We're using the letter mu, which is our letter reserved in statistics for mean. So mu is the mean of the population. So our null hypothesis is that the mean of the population is 7 or 7 feet tall. And the alternative hypothesis, remember, I feel that number is too high. So my alternative isn't that it's just not 7. My alternative is it's definitely less than 7. So I'm hoping that I can get enough evidence to alternatively say that the null hypothesis is not correct, and the alternative hypothesis, there's enough evidence for us to reject the null in favor of the average being under 7 feet tall. To perform a hypothesis test, I would now need to take a sample of these players and find out the average height and see if that average provides enough evidence. So that's the example 2 where I talk about a mean. Example 1 was a proportion, example 2 is a mean, and I have one last example where I'm going to be talking about a standard deviation. So in this example, it talks about the US IQ test. So the creators of the US IQ test claim that the standard deviation is 10 points. There are several interest groups that claim that that number is too low. All right, so we define our variable. So for a population standard deviation, they use the Greek letter sigma. So we define sigma to be the standard deviation of the IQ scores, and our null hypothesis is always using the equal sign. So our null hypothesis is that the population standard deviation is 10, as they claimed, and alternative hypothesis, remember, interest groups claim the number is too low. So alternative would be that it's bigger than 10. So my alternative, H1, is that the standard deviation of the population is larger than 10. So now what do I do? Well, once again, in order to do a hypothesis test, we take a sample of the population, which in this case would be a sample of the IQ scores, and then we find the standard deviation of that sample, and then we see if there's enough evidence now that we can be confident that this sample allows us to refute the claim that the standard deviation is really 10 points. All right, so that's the setup for hypothesis testing. That's sort of the strategy, the order of things you'll be doing things in. So let's do the math. Let's do some numbers for each of these 3 examples so you can see how it plays out. Each of these 3 examples will be using different formulas. So there is an important detail to say, okay, is this a proportion hypothesis test, or is this a mean, hypothesis test? You need to identify which one you're doing, because the technique is going to be a little bit different for each one. All right, so let's go ahead and do the first one, which was about the magician, and I've copied it over here, right? So we have this magician. They give me a coin. They claim that both heads and tails have a 50% likelihood of resulting from a coin flip. And I wonder if the magician is trying to deceive me. So once again, I need to define a variable. In this case, I'll be defining P to be the proportion of tails that result from flips of the coin. Or the magician's null hypothesis, the original claim, is that the coin is 50-50, which means that they claim that 50% of the times, on average, the flips should be tails. And the alternative, which is what my suspicion is that it's not. It's not a 50-50 coin. There's something suspicious going on. All right, so I'm going to collect the evidence, and I want to see if I can be 95% confident that I can dispute the magician's claim. Before I collect the evidence, I need to find out, or need to at least state my confidence level that I'm looking for. So after I collect the evidence, I'm asking, can I be 95% confident that I can dispute the magician's claim? So that's that's the default is 95%. Sort of in statistics, if you don't really have a good reason, you just use 95% as a default. So after I make the statement that I'd like to see if I can be 95% confident in rejecting the magician's claim, then I go ahead and collect my information. Now, the information I collected was, I'm just going to repeat the same. I'm not going to reflip coins, but I flipped the coin 20 times and noted that there were 15 tails and 5 heads. So this is the information from the sample. So I got a sample. In this case, my sample was 20 flips, and I just wrote down how many heads and how many tails. I got 15 tails and 5 heads. So now we need to do a hypothesis test, and all of our technology, our standard technology, all our spreadsheet programs will do the hypothesis testing calculations for us, which is very nice because they're a little bit tedious to do by hand. So I'm going to head over to StatCrunch. Remember, my sample was 15 tails and 5 heads. And also, I am trying to be 90%, 95% confident is what my goal is. Okay, so let me go to StatCrunch. And under statistics, I'm going to be looking at proportion stats. In this chapter, we're only going to have one sample, so we always do one sample. In a later chapter, we'll be comparing two different samples. That's when we do the bottom one, but we're not going to do that for now. We're going to do one sample. And if we just got a bunch of data, I would do the data. And in this case, I was given a summary. So I'll go to summary. So how many successes, how many tails did we get? Well, that was 15. How many observations? In this case, how many times did we flip the coin? The answer was 20. We're going to do a hypothesis test. If you remember from last chapter, we clicked on confidence interval. But in this particular homework assignment, we're going to be doing hypothesis test. We need to know the null hypothesis and the alternative hypothesis. And they're using the A instead of the one here, but I warned you that sometimes they use the A. And just to refresh your memory, if it's not on the top of your head, we are saying that the null hypothesis was the proportion was 50%, and the alternative was the proportion is not equal to 50. And that's what it actually defaults here, hypothesis test. The null hypothesis is that the proportion is equal to 0.5 or 50%. And the alternative is the proportion is not equal to 50%. I could have said less than or greater than, but I'm going to do the not equals for this. There's one other thing that I would recommend you doing where it says output. I'm going to have you click the box here where it says show the critical value. And you'll have to put a significance in there. Significance level is related to the confidence level. It's the 1 minus the confidence level. Since the confidence level was 95%, then 1 minus 95% is 5%. You may have remember doing this many times in the previous chapter where we talked about significance. The alpha level was just 1 minus the confidence level. So success is 15 out of 20. Hypothesis test with a null alternative hypothesis. And I did the option here. You don't have to do this if you want to, but it's going to make things a little easier. I do an optional show critical value with a significance of whatever is appropriate for that problem. It's 0.05 specifically because we chose the confidence level to be 95%. So 5% is the significance of the leftover amount. I'm going to do the compute, and it gives me the readout. So here it says I'm going to be doing a hypothesis test. It summarizes my null and alternative. It says I'm doing a proportion. I got 15 out of 20. The sample proportion, if you do 15 out of 20, by the way, take a calculator out, do 15 out of 20, that is 75%. So that's what the sample proportion is. So our sample had a proportion of 75%. And then we have these statistical calculations of the standard error, the z-statistic, the critical value, and the p-value. All right, so what I did was I copied this readout and I put it into the lecture notes just so we have to flip back and forth. So let me go to the next page. There is, maybe I'll zoom in a little bit. There is the readout that I was just showing you on StatCrunch. All right, so now we need to use these statistical results to decide whether or not we have enough evidence to dispute this claim, this magician's claim that the coin is 50-50. And there are two methods that current statistics classes want you to learn. It's honestly, in my opinion, a little bit of overkill. If you know one method, the other method gives the exact same result. So really just use one method. The homework will be asking you to demonstrate that you know how to use both methods. But ultimately, when it comes down to like a test where you have to show your work and stuff, like a midterm, you could just use the method that you prefer to demonstrate the conclusion. All right, so I have to go through each particular method. We'll do the p-value method first, and then I'll do the test statistic method after that. So on the left-hand side here, we have the p-value method. Let me shrink this down a little bit and scroll. All right, so for the p-value method, we need a p-value, and the p-value is shown right here on the StatCrunch readout. It is the p-value of 0.0253, and that is related to a percentage. So you could say that the p-value is like 2.5%, something like that. That's the probability that I would have gotten the sample results, the 75% or 15 tails out of 20 flips, if the coin was truly a 50-50 coin. So it's pretty unlikely. There's only a 2.5% chance, uh, just by luck or by random happenstance, that I would have resulted in 15 tails if the coin was really a 50-50. So that's kind of what we're doing. So how do we show this? There's a very formulaic way of doing it. So you're supposed to write it out this way, because the stats people get unhappy if you don't write it out in the proper format. So first thing is we write down the p-value, which, as I mentioned before, is the 0.0253. We compare the p-value to the alpha value, the significance level. Remember that we just do 1 minus the c to get the a. So 1 minus the 95% is the 5%. So we have our p-value and we have our significance level, our alpha value. And then we basically have a binary choice. If the p-value is smaller than the alpha value, then we have enough evidence to reject the null hypothesis. However, if the p-value is greater than or equal to the alpha value, the significance value, then we do not have enough evidence to reject the null hypothesis. Remember, there's only two options. Either we have enough evidence to reject the null hypothesis, or we do not have enough evidence to reject the null hypothesis. On your homework, they'll be giving you like different sentences to choose amongst, and they're going to be a little tricky by talking about like things that are in the different format. Like, I really want to say that I'm right and they're wrong or something like that. That's not how it works. Either we have enough evidence to reject the null hypothesis, or we do not have enough evidence to reject the null hypothesis. So that's really what it comes down to. Well, what is our case? Our case, we have a p-value of 0.0253. We have an alpha value of 0.05. So I wrote those down here, p-value of 0.0253, alpha value of 0.05, and the p-value is less than the alpha value. Let me just make this look a little nicer. So the p-value is less than the alpha value, which is our first option right here. If the p-value is less than the alpha value, then we have enough evidence. So our conclusion is, so we have enough evidence to be 95% confident that the magician's claim is incorrect. So that's the p-value method. Let's do the same thing with the test statistic method. All right, so back up here so you can see the readout. Let me get rid of this p-value thing. So the next method is the test statistic method. So the test statistic is the z-stat right here. So the z-stat value is 2.2361. That's the z-stat up here in our readout. And to do the test statistic method, we compare the test statistic to the critical value. Now, we've done critical values before. I'll just remind you, because people may be wondering about this. To do a critical value, I would go to my stat, and I would go to a calculator and go to a normal distribution. Proportions are normal distributions. And then I'm gonna do my like probability to the right, and I have to type in a certain number here, right? There has to be a certain number here. So what number goes in there? Well, if you have a not equals to sign, which we have in our example, we have a not equals to sign. If we have a not equals to sign, then we do z alpha over 2, which means you cut alpha in half. So you have one above and one below. If you are just using a less than sign or a greater than sign, maybe I shouldn't use two lines because that may look like an equal. If you just have a less than sign or a greater than sign, then you just do z alpha. In our case, our alpha level is 0.05, so we do z of 0.05 divided by 2. So I'll go to StatCrunch. I'm going to do 0.05 divided by 2. I think I can do this. No, I can't. So I will just, maybe it will. I haven't done this before, so I'm going to try it now. Let's see if it lets me do 0.05 divided by 2 right on the screen. And then I need to do greater than. That's my z value of 2. So it didn't. Oh, I did 0.5 over 2. So it does work. I just typed in the wrong number. 0.05 divided by 2. My alpha value is 0.05. I divide by 2 and I compute. Yeah, so it worked out. It does the math for us. So 1.9599, that is the critical value, the z alpha over 2 value. And that is, in fact, what it gives up here when it says, what is the critical value? Now it says 1.9599, but that rounds to the same number, 1.96. So this method of finding the Z alpha over 2 method, getting 1.9599, which is 1.96, it's the same as the readout from StatCrunch, which is, whoops, wrong one, which is why I had you do that optional at the bottom, so that it would give you this one for free. So let me hide this and open up my proportion. So there's the 1.9599 number. That's our critical value, our Z alpha over 2 value. All right, back to this one. So we have our critical Z value, which is 1.96 if you round it. Okay, so we're going to be comparing now the Z-stat and the critical Z value, whether you got it from the readout or whether you did it by hand, or did it separately, I guess, using the normal distribution. Okay, one other little bitty thing. I mean, stats books and stat programs are all a little bit different, so I have to kind of warn you about these little idiosyncrasies. Because this is a not equals, we call this a two-tailed test. And because it's a two-tailed test, they're going to use a plus or minus. So they're going to say like this. It could be 1.96 all the way to the right, or it could be 1.96 all the way to the left. So one is a positive 1.96, and then there's a negative 1.96. It'll be pretty obvious when you start doing the homework, and it'll ask you for the two critical values, and it's just the same number, one with a positive, one with a negative. So how do we now use the test statistic method? Well, once again, we're going to compare. In the p-value method, we compared the p-value and the alpha value. In the test statistic method, we're going to compare the test statistic and the critical value. So the test statistic, if the test statistic is greater than the critical value, then we have enough evidence to reject the null hypothesis. If the test statistic is less than or equal to the critical value, we do not have enough evidence to reject the whole null hypothesis. You might want to make note that the part that says that we do have enough evidence, the sign here is greater than that we do have enough evidence. But on the p-value method, it's the opposite sign, that we do have enough evidence. So I think it's confusing if you haven't done these before and you don't have like a chart in front of you to remind you about the less than or greater than stuff like that. That sometimes is where students get a little stuck on when they're first learning the hypothesis testing stuff. So what is our test statistic? Well, that's the 2.23 number. What's our critical value? That's the 1.9 number. So I wrote them down here, test statistic and critical value. That looks really messy. So test statistic and critical value. The test statistic was the 2 number, and the critical value was the 1.96 number. And this is the test statistic is greater than the critical value. So if you look at back up here, this is where the greater than sign, if the test statistic is greater than the critical value, then we do have enough evidence to reject the hypothesis, exactly like we concluded using the p-value method. And our conclusion is exactly the same. Our conclusion is, so now we have enough evidence to be 95% confident that the magician's claim is incorrect. Okay, one little detail about the test statistic method. You may have noticed that I have these extra bars here and here, like the bars around the test statistic and the critical value. Those are absolute value bars. So if you do have a negative, you just ignore it, right? So if it was a negative 2.2, you just say it's 2.2. That's the only reason I put the absolute value bars there, just to remind you that negative and positive don't matter in using the test statistic method. You just look at the numbers, the positive versions of the numbers. All right, so now let's talk about our conclusion. We know we have enough evidence to be 95% confident that we can reject the magician's claim. So what are we saying? So this is getting into how to properly describe our conclusion using the context of this scenario. So I'm just going to remind you that we are claiming to be 95% confident the magician is wrong. It still is possible for us to get 15 tails out of 20 flips with a coin that is genuinely 50-50. But we are saying that getting 15 tails out of 20 from supposedly a genuine 50-50 coin is so unlikely that we are confident it's not a coincidence, it's not luck, it's not random chance. We have very good evidence that the magician's claim is incorrect. So this is the gist of how we want to write out our conclusion in clear language that's precise. We have good evidence that the magician's claim can be rejected. What kind of good evidence do we have? We have evidence that 15 tails and 20 flips is so unlikely that we are now 95% confident that the magician is incorrect. All right, so that's how we explain the meaning of the results of our hypothesis test. So just to emphasize this just a little bit, like 15 out of 20 sounds like a lot. It sounds like, oh, that seems like too many. What if we got 14 tails out of 20? Would that be enough to reject the hypothesis that the magician is correct? What if we got 13? Is 13 and like what's the where like how do we know how many is enough, right? I mean, I guess most people would say if you have 19 out of 20, that's like really probably enough evidence. And we saw here using our statistics that 15 out of 20 actually gives us enough evidence to be 95% confident that the magician's claim is incorrect. I mean, it does give us a 5% chance that we are incorrect, but it's 95% confident. It's pretty darn confident. All right. If we got 14 tails, would that be enough evidence? If we got 13 tails, would that be enough evidence? Instead of just trying to kind of guess it out or intuit it out, we actually have mathematical formulas that can answer these questions very simply. And we could just go over to our StatCrunch. And right now we said we got 15 out of 20. I could just go here and edit this thing. And I could say, well, what if I got only 14 out of 20? It's going to wait for a second before it gives me a chance to change that. Okay, there it is. 14 out of 20. So I'll keep everything else the same. Suppose I only got 14 tails, right? Suppose that was the result of the sample that I did. So I do my little compute. Notice the p-value is not the same before. The p-value is 0.07. And if you think about the p-value method, the p-value was 0.025 before, and 0.025 was less than 5%. But now our p-value, 0.07, is higher than 5%. So this is now in the other thing where if the p-value is greater than the alpha value, we do not have enough evidence. And once again, we can use the test statistic and critical value method. So the test statistic right here, the z-stat is the test statistic. That was 1.7, and the critical value is 1.96, and the z-stat is not greater than the critical value. So once again, we don't have enough evidence because the test statistic is not greater than the critical value. So we can answer the question just by using the exact same formulas and plugging in the numbers that we actually got this time, which was 14. This particular sample does not provide enough evidence, and you can plug in 13 or other kind of numbers to see if you have enough evidence. But you no longer have to sort of make an argument like, well, I feel it's too many. You can do some actual mathematical formulas and say, look, math formula says that I can be 95% confident that this is true, or I cannot be 95% confident that this is true. All right, so that was my detailed, hopefully detailed explanation about hypothesis testing for a proportion. All right, so maybe time for a break, but if you want to come back for the break or just keep going, I'm now going to do the same thing for a population mean. So example 1 was about a population proportion. Now we're going to be looking at hypothesis testing for a population mean. All right, so the example that I gave a couple pages ago was suppose my friend says that the average height of an NBA player is over 7 feet tall, but I feel that this number is too high. All right. What are the null and alternative hypotheses? Well, we need to define a variable. So always make sure you define a variable. In this case, we're going to use the variable mu. That's the letter that stats people use for the population mean. So our null hypothesis, which always uses an equal sign, is that the mu is 7 feet. And the alternative hypothesis is either a less than or greater than or not equal to. How do we decide? Well, I feel the number is too high. So as before, if I think the number is too high, then my alternative would be that the mean is lower than 7 feet. So my null hypothesis and my alternative hypothesis are right here. I did convert them into inches. So 7 feet is the same as 84 inches. And I did that because it's much easier to average inches together. Like if you had to average 7 feet, 3 inches, and 6 feet, 11 inches together, it's confusing because it's a mixture of feet and inches. So I just converted everything over to inches just to make sure it's easier to add up inches and divide by the number of things I added together. So just for convenience of doing the math, I converted things to inches. We'll do our conclusion in feet, of course, because that was the question. The question was about feet. All right, so to perform a hypothesis test, I need to take a sample of these NBA players and find the average height of those players. So in order to perform a hypothesis test, I define a variable, I write down my null and alternative hypotheses, and then I need to take a random sample or a sample of the population to test to see if I have enough evidence to reject the null hypothesis claim. Notice that before I collect the data, I must choose a confidence level. You're not allowed to choose a confidence level after you've collected the data. There's several reasons for that. One of the most important things is there's a lot of cheating that can go on if you first do the sample and then choose the confidence level. I'm not going to go into all the details of why this is really a taboo in statistics. You take my word for it for now, or we can have a longer conversation about why this is not. It's called p hacking is the name of that. It's actually so bad that it's got a name, and a lot of like things you see on the news are results of p hacking, and they're really unreliable. All right, I've gone on a segue. So let's get back to the focus. Before I collect the data, I must choose a confidence level. And for this problem, I didn't do any pre-selecting. For this example, I chose a confidence level of 99%. I hope I can be 99% that I'm able to refute I think my friend is way wrong, right? So I think before I do any data collection, I think I can be 99% confident that she is saying the average height is over 7 feet tall is not correct. Now, she says the average height is over 7, but the null hypothesis always has an equal sign, right? So even though the claim is it's over 7 feet, I still need to make an equal sign. So I say it's equal to 7, and the alternative is definitely less than 7. So she sort of gets the greater than 7 for free because my alternative is only that it's less than 7. All right. So now once I have my statements down and I chose my confidence level, the next thing I do is I do my collection of the data. So I went on StatCrunch. I found a data set called Math 110 NBA Roster 2021, which has all kinds of data statistics about the NBA basketball players in 2021. It has 558 players in the year 2021. I took a random sample of 50 players and I used StatCrunch to compute the mean and the standard deviation. So I get a mean, which is written as X bar. Again, sometimes PDFs don't put my little bars and stuff in there. So X bar is 79.24. That's 79.24. That's supposed to be a bar there. Inches, which is the same as 6.6 feet. And the standard deviation S was 3.1852 inches, which in feet world is 0.2654 feet. All right. So in order to calculate, oops, this is a typo. In order to calculate, oh no, that's right. In order to calculate the p-value and test statistic, we need to decide whether the z-stats hypothesis test can be used or the t-stats hypothesis test can be used. So as I mentioned before, when you're doing like mean hypothesis testing, it's going to be a little bit different than when you do proportion hypothesis testing, and the standard deviation hypothesis testing will be a little bit different as well. So you really got to like follow the format for your particular type of hypothesis testing. So once again, in order to do the hypothesis test, in order to calculate the p-value and test statistic, we need to decide whether to use the z-stats or the t-stats. And it's pretty simple. It's pretty simple. There's two possibilities. If we do know the population standard deviation, which is the sigma thing, then we use z-stats. If we do not know the population standard deviation, we use the t-stats. So the formulas are different depending on whether you know the population standard deviation, which is that sigma thing, or if you don't know the population standard deviation, right? So in this particular case, we were not told the population standard deviation. Maybe we could do some work to try to figure it out, but in the problem we have, there's no information about what the population standard deviation sigma is going to be. So in this particular case, we're going to have to use the t-stats method because we do not know the population standard deviation. A couple little notes. With sampling distributions and other statistical methods like this one here using the t-stats method, we need to know that either the population is normally distributed, or we need to choose a sample size greater than 30. You may remember this from doing our confidence intervals, but we need either a normal population, normally distributed population, or we need a sample size at least bigger than 30. All right. So once again, in this situation, we do not know the sigma, the population standard deviation, so we use the t-stats hypothesis test. And even though we don't know the population is normally distributed, we do have a sample size of 50. Remember, on StatCrunch, I used a sample size of 50, so I have enough to get over the 30 threshold, which will give me results that I can actually make conclusions on. Okay, so I'm going to do it on the next page. I'm going to show you the StatCrunch readout and the hypothesis test. And of course, we'll show you both methods using the p-value method and the t-statistic method. All right, here we go. All right, so this is the readout. I'll show you how you get the readout. So I go to StatCrunch. Let me get rid of this little thing here. I go to stat, and you'll see there's a z-stats and a t-stats. So if I'm doing the z-stats version, when I know the population standard deviation, I'd use this one. In this case, we're using the t-stats method because we do not know the population standard deviation. Once again, we're doing one sample in this chapter. Later chapters do two samples. And then if I was given the raw data, I would do this one. I'm given a summary, so I'll go to summary. And then I have to type in the sample mean, which I'm going to have to get off of here. Sample mean, oops, sorry, on the previous page. Sample mean was, here we go. Sample mean, blue over here, was 79.24 inches or 6.6033 feet. And the standard deviation was 3.1852. So 79.24, 79. My computer does this every now and then. 79.24. My sample standard deviation was 3.1852. I'm doing inches again just because it makes the math easier. Instead of feet and inches together, it gets difficult to average things. 3.1852. All right. Well, that's right. 3.1852. Okay. And then what was the size of the sample? I do believe I chose 50 players. So I'll just double check. Oh yeah, 50 players right here. I chose 50 players to do my calculations with. Okay, I found it. Hypothesis test. I want my null hypothesis. Now, my null hypothesis wasn't zero. In fact, it wasn't even my hypothesis. It was my friend. My friend's null hypothesis was that it was 6 feet, which is the same as 84 inches. Right? My null hypothesis was 84 inches. And then my alternative is that it's less than 84 inches, less than 7 feet. 7 feet, by the way, is the same as 84 inches. So I'm going to choose the less than sign. So here's the less than sign right here. So null is equal to 84. Alternative is less than 84. I'm going to choose my critical value. Now, the significance is not 0.05 because I'm not doing a 95% confidence test, right? And my hypothesis level, my confidence level was not 95. If you recall, I'm choosing a confidence level to be 99%, 0.99. So then the alpha value would be the 1% left over. So C is 99%. The alpha is just the 1 minus C, which would be, in this case, 1%. So let me put in my 1% here. There we go. All right, so got all the stuff set up. My sample mean, sample standard deviation, sample size, null alternative, and my significance level. And here is the readout. It gives the mean, the sample mean, standard error, degrees of freedom. DF is degrees of freedom. You don't have to worry too much about unless you're doing other calculations by hand, but that's what the DF stands for, degrees of freedom. We have our test statistic, our t-stat statistic, our critical value, and our p-value. And I've just copied and pasted this onto the lecture notes. So that's what this readout is over here. I'll zoom in a little bit so you can see that it's really the same thing. All right. And if they ask you degrees of freedom, by the way, the reason why the degrees of freedom is 49 is that the degrees of freedom is always one less than the sample size. So the sample size in our case was 50. That was the number of players that I used to find the sample mean. And then the degrees of freedom is just n minus 1, which in this case is 50 minus 1, which is how we got to 49. So if you need to calculate the degrees of freedom, it's just one less than the sample size. That's all it is. It's one of these kind of older statistical hangover things that they haven't got rid of yet. But it's in some formulas, and now you know what it means. All right, so once we get our readout from our StatCrunch or whatever program you're using, we can do either the p-value method or the test statistics method. And now it's going to look very similar to what we did before. Once we have the readout, the methods are going to look very similar. So p-value method, we'll do that one first. We are literally just comparing the p-value to the alpha value. Our p-value right here is less than 0.0001, so very, very small. So small that it's less than, they don't even have a number for it. It's less than 0.0001. So the p-value is, minute, 0.000, even more zeros maybe. And the alpha value, remember that was the 1 minus 99%, that's the 1%. And once again, if the p-value is less than the alpha value, we have enough evidence to reject. If the p-value is greater than or equal to alpha, we do not have enough evidence to reject. In our case, what do we have? We have a p-value of 0.001. Actually, we have a p-value of less than 0.001, but I just put it as that. And our alpha value is 1%. So our p-value is less than our alpha value. Let me move me over here, maybe. Right? So our p-value, just trying to get on screen, p-value was 0.0001 or even less than that. Our alpha value was 1%. So our p-value is less than our alpha value. That is, in fact, this first guy right here, just like before. So now we have enough evidence to reject the null hypothesis. So we do have enough evidence to reject, we do have enough evidence to be 99% confident in rejecting our friend's claim, right? So we can be 99% confident that our friend's claim is incorrect. Now, I'll just kind of remind you about the way it's written out, the way that you're supposed to interpret this. We are claiming to be 99% confident that our friend is wrong. It's still possible for the overall average of NBA players' heights to be taller than 7 feet. But we are saying that getting this random sample of 50 NBA players whose average height was 6.6033 feet, which is the same as, the number of inches here. I just converted it, the 79.24 inches, that's the 6.60 number. Sorry, I didn't explain that before. But we are saying down here that getting a random sample of 50 NBA players who average height is 6.6033 feet, when the actual mean is supposed to be 7 feet, is so unlikely that I'm confident it's not a coincidence. It's not luck. It's not random chance. How confident am I? I'm 99% confident. We have very good evidence that my friend's claim is incorrect. We have such good evidence that my friend's claim is incorrect. I am 99% confident that my friend's claim can be rejected. And the test statistic method is just the same thing with the same conclusion, except we're comparing two different things. With the test statistic method, we compare the test statistic with the critical value. The test statistic, if I erase this guy over here, the test statistic is right here. It's the negative 10.56. The critical value is right here, negative 2.4. And I'm just comparing those two, right? So if the test statistic is bigger than the critical value, then we have enough evidence to reject. If the test statistic is less than the critical value, we do not have enough evidence. So the test statistic, I'm finding it difficult to put everything on the screen. The test statistic was the negative 10.56, and the critical value is negative 2.409. Remember, I'm using absolute values, so we ignore the negative signs. So the 10 number is greater than the 2 number. So we have a test statistic, if we ignore the negative signs, which is bigger than the critical value number. So that is enough evidence, right? So remember, if we have a greater than thing right here, whoops, here, if test stick is greater than the critical value, then we have enough evidence to reject. And everything I said before, the conclusions are always the same, whichever method you use. So we're 99% confident that we have enough evidence to reject our friend's claim that the basketball players have an average height of at least 7 feet. All right, so that is the hypothesis testing with a mean. All right, we have one more to do, which is hypothesis testing with a standard deviation. Okay, so my example for hypothesis testing for a population standard deviation was about the creators of the US IQ test. They claim that the standard deviation of the test is 10 points. But there are several interest groups who claim that number is too low. So once again, we define a variable. In this case, our variable is sigma, because that's the letter they use in stats for the population standard deviation. And hypothesis is that the test creators claim that the sigma value, the population standard deviation is 10. And the alternative, I wrote greater than here. Why did I write a greater than on this particular problem? I wrote a greater than because the interest claim that number is too low. So if these people think the number is too low, then they think the actual number is higher than 10. So my alternative is that the alpha value or the sigma value is greater than 10. All right, so now I have my null alternative hypothesis written down. I have my variable written down. To perform a hypothesis test, I now take a random sample of IQ scores and I compute the standard deviation of that sample. Before I collect the data, I'm supposed to choose a confidence level. The default in statistical calculations and hypotheses tests is 95%. So I'll just choose 95% because it's the default. That's normally what people would choose. And on another discussion, we could talk about why choosing CDB different levels, but there may be specific reasons why we need more confidence, or we don't care if we have enough confidence, as much confidence. So right now, we're just going to choose 95%, so I can keep this on sort of point in terms of hypothesis testing for a population standard deviation. All right, so I've chosen my confidence level. I got my null alternative hypothesis. I got my sigma, and now I need to collect some data. So on StatCrunch, I found the data set. It's called Ruby Simulating IQ Scores, which has 5,000 IQ scores on it. And I use StatCrunch to choose a random sample of 31 IQ scores. and I use StatCrunch to compute the standard deviation equal to 11.90. So let me show you real quickly how to get that on StatCrunch. So let me hide this guy right here. So I'm going to go to Stat, and to do the standard deviation on StatCrunch, you have to do the variance. Variance is just the square of the standard deviation, so we can translate it and do the variance test just like we do the standard deviation test. Once again, we have one sample, and we don't have data. Like if I had the data, suppose they give me a bunch of data, so I had one. Oops, give it a sec for it to let me type in here. If I had 1 and 2 and 3 and 4 and stuff like that, right? If I had data, then when I went to stat and variance, then I would say I have one sample with data, and it would ask me where's the data. So I would say the data is in var1, whatever the column the data is in, and it would do all the math the same way, right? So I mean, this isn't the data. I just kind of made up the numbers 1, 2, 3, 4. But I was going to show you like it's the same if you have the data instead of the summary. You just choose literally data instead of summary. But this is not the real data. I have the summary of stuff. So once again, when I went on StatCrunch to find the sample, I got a random sample of 31 scores, and the 31 scores had a sample standard deviation of 11.90. So I just collected and showed you the summary because it's just easier to do things. So once again, I go to stat. The variance is the same calculation as for standard deviation. One sample with summary. Boom. Sample variance. Sample variance. Let me go back here. Now it says right here. Let me maybe circle it a little bit here. Maybe I didn't make this really clear on here, but the sample, a random sample of 31 IQ scores had a sample standard deviation of 11.90. So S is 11.90, and that came from our original null hypothesis of 10. And the reason why I'm trying to emphasize this is, remember, this is a standard deviation. This is not a variance. This is a standard deviation, not a variance. Deviation, right? So when I plug the numbers into StatCrunch, I need to square everything because that's how you get the variance from the standard deviation. So 11.90 was my sample standard deviation. So when I go to type in the sample variance, I'm just going to hit 11.90, and then I'll just say squared. You can do it separately in the calculator, but as we saw before, you could just type in the square here for and StatCrunch will figure it out for us. The sample size, if you don't remember, was 31. You can double check that there were 31 numbers I pulled off to take the sample variance from. I need a hypothesis test. Remember, it's the square of sigma. So our null hypothesis was that sigma was 10. So that means our null hypothesis, or our sigma squared, is going to be 10 squared. And our alternative hypothesis, let's double check. I think it was a less than sign. Oh no, it's a greater than sign. So the alternative hypothesis was sigma is greater than 10 because the interest groups think that the number is too low. So what they're saying is it should be higher than 10. So sigma greater than 10 is all alternative hypothesis. In this case, it's sigma squared is greater than 10 squared, which I guess is 100. I could have typed in 100 there. I will do the critical value. And since we chose 95%, the significance is 5%. That's what it defaults to because most of the hypothesis testing is done at a significance level of 5%. In other words, a confidence level at 95%. So we'll leave that there. Sample variance, sample size, hypothesis test is equal to for the null hypothesis. And it shouldn't be greater than. It shouldn't be not equal to. It should be greater than. I talked about it, but never selected it. So once again, I just double check everything because I make little mistakes just like that. You may identify with making little mistakes, and it kind of throws you off a lot. So yeah, that should be all not correct. I do compute, and it tells me the variance, sample variance. This was the 11.90 squared My degrees of freedom is 30 because my sample size was 31. 31 minus 1 is 30. This is the test statistic, which is 42.483. It's called chi-squared when you're doing standard deviations. You don't have to worry about a language if you want to. Here's the critical number and the p-value, right? So that's all the information I got from the StatCrunch. And of course, you could do all kinds of stuff by hand, but this is my recommendation for doing these problems here. Okay, so I show you now the readout. So here's the readout. I made it small. So our sample variance, our sigma squared was 100 and alternative was greater than 100. And these are the same numbers that I just showed you from the StatCrunch reading. I just literally copied and pasted it here, so I wouldn't have to like jump back and forth. Once again, we have two methods, p-value method, test statistic method. I'll do them reverse this time just to be different. The test statistic method, we are comparing the test statistic and the critical value. The test statistic is right here. The critical value is right here. We're seeing which one is bigger than the other. The test statistic is 42. And the critical value is 43. So the test statistic is less than the critical value. According to what we saw before, and I can show you again if you'd like, if the statistic is bigger than the critical value, then we reject. If the test statistic is smaller than the critical value, then we do not reject, right? So in this case, the critical value or the test statistic is lower than the critical value. So we do not have enough evidence to be 95% confident that the standard deviation is actually more than 10, or is not equal to 10, right? And the p-value method, we're comparing the p-value and the alpha value. The p-value is this readout over here. It's 0.065. So that's our p-value right there. Our alpha value was the 5%. Remember, 1 minus 95% is 5%. So our alpha value is 5%. So now we compare the p-value and the alpha value. The p-value is 0.065, which is like 6.5%. The alpha value is 0.05, which is 5%. It is not less than. If the p-value is less than the alpha value, we reject. If the p-value is greater than the alpha value, we do not reject. So once again, using either method, you get the same result. So we do not have enough evidence to be 95% confident that we can reject the null hypothesis that the IQ scores is equal to 10. Okay, or in fact, we can do it in favor of the fact that we now have enough evidence to reject the null hypothesis in favor of the standard deviation being larger than 10. Okay, so to try to once again just put this into our clear, concise language, we are saying that this sample does not provide enough evidence, right? We are saying that we cannot be 95% confident that our friend is wrong, or that, I guess this should be our friend. This should be that the IQ test makers. That is definitely a copy paste error. We cannot be 95% confident that the IQ test makers are wrong. It's still possible for the standard deviation of IQ scores to be more than 10. We just don't have enough evidence to make that claim confidently. We are saying that our random sample of 31 IQ test scores did not provide enough evidence for us to confidently reject the claim that the standard deviation of IQ scores is really 10, right? So it's whether we have enough evidence to reject the null hypothesis in favor of the alternative hypothesis, or whether we do not have enough evidence to reject the null hypothesis in favor of the alternative hypothesis. So my friends, is hypothesis testing, 3 different examples, one with proportions, one with mean, and one with standard deviation. A lot of similarities, but you'll notice there are definitely significant differences in those 3 versions. And for each of those 3 versions, we use the p-value method and the test statistic method to determine the same conclusion and try to write a clear conclusion at the end of what our test results tell us about the context, the scenario that we're dealing with. Okay, we have one last bit to do, which is much shorter, right? The meat of chapter 8 is all about hypothesis testing. We do have one last thing, which is about errors. And I said this is a minor thing. It won't take very long at all. So our last major learning objective for 8.1 through 8.4 is to identify and explain type 1 and type 2 errors in hypothesis testing. So the stats people just kind of emphasize that, being 95% confident still means there's a possibility that we're incorrect, right? I'm 95% confident that the magician's coin was not a 50-50 coin, but I'm not 100% confident, right? I'm 95% confident, right? Like we can be 99% confident that our friends claim that NBA players' height is taller than 7 feet is incorrect. But that means we also have a possibility that the friend was correct, and our evidence just didn't show that, right? So it's definitely possible, although we are 99% confident that we can reject their claim, or we can be 95% confident that we cannot reject the claim, right? We cannot be 95% confident if we were to reject the claim that the standard deviation is 10 points, right? So either we have enough evidence or we do not have enough. We are confident we have enough evidence, or we are not confident we have enough evidence. So just to make sure that whether we reject the null hypothesis or we fail to reject the null hypothesis. So this one here, by the way, was the reject the null hypothesis. And this one here was a fail to reject. We don't have enough evidence. I mean, we didn't fail, and we just didn't get enough evidence to reject it, right? Which is not our fault. It's just what happened, right? That's just the way the math people say it, right? Either you reject or you fail to reject. But of course, because we don't have 100% confidence in any of these situations, our conclusions could still be wrong. All right, so that's the setup for type 1 and type 2 errors. So let's talk about what the type 1 and type 2 errors are. So the type 1 error occurs when HO is actually correct. By the way, a type 2 error occurs when H0 is actually wrong. So that's the difference between type 1 and type 2 errors. A lot of students have a hard time differentiating between the two of them or get them confused. Type 1 is HO is actually correct. In the real truth of the world, the null hypothesis is correct for type 1 error. And in the real truth of the world, for a type 2 error, the null hypothesis is actually wrong. Okay, so what is the error? Well, a type 1 error is, remember, the null hypothesis is actually correct, and our hypothesis test gives us enough evidence to claim that the null hypothesis is wrong. But that's a mistake because we now know that HO is actually correct, but we got the really rare situation where we got enough evidence to be like 95% confident that we could claim that the null hypothesis is wrong, but it turned out that that 5% was actually the correct, right? We were only 95% confident, which means it's possible that we were wrong. So type 1 error is you reject the null hypothesis, but you're wrong, right? It's actually that the null hypothesis was correct. Type 2 error is the same idea, but the other way. So this occurs when the null hypothesis is actually wrong. And so what would be our error in that situation? Well, if HO is actually wrong and a hypothesis test doesn't give enough evidence to reject the null hypothesis, remember the null hypothesis is actually wrong for a type 2 error. If we do our hypothesis testing and we don't give enough evidence to conclude that HO is wrong, then we fail to reject HO when in fact we should have been rejecting HO because it was actually wrong. Again, it's not our fault. It's just what the evidence provided, right? The sample either provides enough evidence or doesn't provide enough evidence. If the sample doesn't provide enough evidence to reject the HO when HO was actually supposed to be wrong, that's called a type 2 error. So they want you to just be able to identify type 1 and type 2 errors. They're not going to ask you any like weird calculations with that kind of stuff. They just want you to understand what those types of errors are, that they're possible, and what they are labeled as. The only sort of modest kind of calculation they have you do is with this thing called power. So some technical stuff you just have to write down or review is that this is called a beta. The beta is the probability of a type 2 error. So remember, it's definitely possible that HO was wrong, but we didn't have enough evidence to reject HO. That's a type 2 error. So beta represents the probability of making a type 2 error. Now they only define beta to talk about the power. So the power is 1 minus beta. That's the probability of correctly rejecting HO when it's actually true that HO is correct. So power is good, right? Power is good because it's the likelihood of correctly rejecting a null hypothesis. That's kind of the summary that I would suggest because it's all convoluted. The wording is all weird, right? So the summary I like to have students kind of just ponder is that power is good because it's the likelihood of correctly rejecting a null hypothesis. I'll put some numbers in here just to help give it some more concrete stuff. Suppose that the probability, suppose has an ENIT, suppose the probability of a type 2 error is 10%. I'm not going to talk about how I got that number. I'll just do an example so you have numbers here. In other words, we're saying that beta is equal to 10%, right? So suppose that we have the probability of a type 2 error is 10%. So the power would be, that would just be the 1 minus thing, just the leftover part. So the power is 1 minus beta. Since the beta was 10%, the power is 90%. So we have a 90% probability of correctly rejecting a null hypothesis using this particular statistical testing method. So that's the only other thing in chapter 8 that is significant that you'll have to know to answer the homework questions and the chapter test question. Kind of like that. Okay, well, that is the end of this very long video. Just go back up to the very first page there. Read off the main learning objectives. So this video focused on how to construct a hypothesis test for 3 different population parameters, a proportion, a mean, and a standard deviation. We determined the conclusion of each of those hypothesis tests using 2 different methods. One was called the p-value method. The other was called the test statistic method. We tried to clearly and precisely explain what our conclusion of the hypothesis told us about the scenario or the context of the problem situation. And the last thing we did was we identified and explained the type 1 and type 2 errors that are possible in hypothesis testing. All right, please reach out if you have any questions, if you have any other kinds of scenarios that you'd like to talk about, or if you just like some more information, some more background about some of the things that I didn't explain all the way just because this video is already getting too long. And I wanted to stay focused. So please let me know if I can help out in any way, and I hope you have a very enjoyable day.